I am Eric Crosby. This meeting is usually led by Dr. Heather Nusky, but she is out of the office on maternity leave. Congratulations to her on her new daughter. Um, but yeah, we'll be recording this meeting, so it's available to everyone, like I mentioned. And then I'll just introduce Ian here, so you guys are all aware of his research and what we're focused on today. So Dr. Ian Barnett is an assistant professor of biostatistics at the University of Pennsylvania, specializing in the development of statistical methods for analyzing high-dimensional and correlated data. Dr. Barnett's group has developed the methods and software behind numerous industry-standard data processing pipelines. These are widely in use and for the analysis of sensor data collected in mobile health studies. And the pipelines are capable of modeling sparse, missing, multivariate, and intensive longitudinal data, and translating these data into clinically actionable measurements of behavior. As a founder of the Penn Unit for Mobile App Sensing, PUMAS, Dr. Barnett is dedicated to advancing digital phenotyping to understanding diseases, complexities, and enhancing personalized patient care. So please join me in welcoming Dr. Ian Barnett.
Thanks, Eric. Great, I'll take it from here. So again, I do apologize for the background. I'm sitting in Vancouver in their airport right now. I was just at AAAI in Vancouver this year. I believe it's like the advancement for, actually the Association for the Advancement in Artificial Intelligence, something like that. Anyway, I gave a talk yesterday and I'm flying back today. So the timing works out. My flight is in 2 hours from now. So I just hope that the Wi-Fi will hold up and that you guys can hear me fine throughout. But I'll get going. Let me share my screen. So I'm just kind of going to give an overview. I'll also check chat periodically, but if I miss anything, do feel free to just pipe up if anybody has questions throughout. I'm going to be presenting kind of a wide array of work that has been developed in my group, all related to the analysis of smartphone data. But to start with, I'll talk about the importance of measuring behavioral variability. I mean, when I talk about some of the methods that we've developed later on for longitudinal and temporal data, the essence of it is it's worth doing that when there is behavioral variability within a person over time that's meaningful. So just to kind of establish that, I think we all kind of know that is true, that it is important, but I'll touch on some past literature to just establish how important it can be. Now, I am no psychiatrist. I'm a statistician at heart and in training. So this is definitely more of a surface level read of the literature there, but I should at least be able to impart the primary points that come from this. So yeah, what I mean by behavioral variability, I'm talking about both, day to day. So if we're measuring behavioral features daily over a long follow-up duration for any given individual, how variable are those measures from one day to the next, but also within a day? So, is there diurnal variation and whatnot? So, and what I'm going to kind of set the stage for is, and I think maybe I'm preaching to the choir a little bit here, but mobile health is a great way of either smartphone data or wearable device data. These are great ways of collecting continuous time data. Like if you want to capture diurnal variability, which is maybe that requires the highest resolution, temporal resolution in your data, you'll absolutely need some kind of wearable device or smartphone data. So that's where I'm going, ultimately setting the stage for why we need this kind of data. But to get there, I'm going to just focus, for example, on one type of behavior, sleep. Now, throughout my talk today, I'll talk about different domains of behavior, be it mobility, activity, sleep, social activity. all of which we try to estimate with smartphone data. But just as an illustrative example, let's start with sleep. So, a lot of studies might, at baseline, a common questionnaire would be the PSQI, the Pittsburgh Sleep Quality Index, which might be given at baseline, which it asks these example questions, right? When have you usually gone to bed? How many hours of sleep do you get per night during the past month? How would you rate your sleep quality overall? But you'll note that all of these are essentially trying to get at average behavior and not day-to-day variability. Whereas we do know that there are plenty of research that supports the idea that day-to-day variability in sleep is immensely important and related to a variety of outcomes. So, for example, increased sleep duration is associated with increased positive affect in the following day in children, and probably that's universally true. But whether or not you sleep your average sleep is, say, high or low, if you follow someone over time and they have a good night's sleep, it's going to affect the following day. But that might not have any implications on how they feel 2 weeks from that day. So clearly it's important to not just get that baseline questionnaire, but to maybe have that night-to-night estimate of sleep. There's been mice studies that also look at kind of the proximal effects of sleep deprivation. And also this bottom study was a huge cohort of participants, which the conclusion of this study was essentially that insomnia and anxiety depression had this kind of bidirectional relationship, so a bidirectional temporal relationship, right? So you have insomnia, which heightens your anxiety and self-reported depression, but also vice versa. The day before, if you're experiencing a lot of anxiety, then maybe you're having trouble sleeping and you have insomnia. And so there's a lot of evidence that's kind of pointing to the really important proximal temporal relationship between sleep and a variety of important clinical outcomes. So this is something that with the PSQI alone you would not be able to kind of make any proximal the PSQI alone is not going to give us any information that would allude to any proximal effect. So here's another one, is that sleep loss prior to assessment the night before. This is a little bit more complicated. There's like an interaction term, but people who had suicide attempt history, if they had, if you look at this plot, if they had high sleep loss, then the severity of their ideation was higher the next day. Whereas if you had no history, there was kind of no relationship. So there was like an interaction with your suicide history. But again, this is just demonstrating this proximal relationship between sleep and, in this case, a suicidal ideation. So what are we taking from this? As I've said a couple times now, acute changes in sleep, they may precipitate a variety of important clinically related outcomes. And single sleep measurements at baseline are just not going to capture that. So how do we go about assessing sleep frequently, say over the course of duration of a longitudinal study? And right, so up until now, actually, I've been talking about variability in day-to-day assessments. In the beginning, I also alluded to we could get at a finer resolution than just day-to-day measurements. What if we want to look over the course of within a day, diurnal variation? That too, we see that there's going to be meaningful variation. So this was an interesting study where they did self-report of mood. In this case, the y-axis, you can kind of think of this as a standardized affect. And what they did is they looked at, okay, let's look at depressed patients as the solid line here. What was their self-reported positive affect at 8:15 a.m.? Now, yeah, note this here at the bottom is that they were put on the same scale just so they could be plotted together. But obviously, the positive affect was higher for the people who were not depressed. But this is just meant to show that, like, if you were to ask your depressed subjects closer to midday how they were feeling, they're generally feeling better about themselves, right? But what if you had instead administered that questionnaire at 10 p.m.? Well, you might get a very different picture, a drastically different picture for the depressed subjects. And even amongst healthy subjects, there's variability over the course of the day, maybe less lopsided than what we're seeing in the depressed subjects. But if you look at this, I would be very wary if you're designing a study and just saying like, okay, I'm going to get their daily, like, how are they feeling this day? Well, you need some nuance. You got to say, well, at what time of day did you ask that question? That can have a huge impact on the response, which, so it might not even be enough in some cases to just get a single assessment over the course of the day, because now you're not allowed, you're getting a single snapshot of this curve where there could be a lot of variability with over the course of the day, depending on when you would ask it. So we can see that not only is there significant day-to-day variability in many cases, but within the course of the day, that is something that we'd want to be able to measure as well. So how do we measure that? This is where I advocate for smartphone data. So, again, I think on this call, everyone is maybe somewhat pretty acquainted already with mHealth. I'm definitely, when I think of personally the state of mHealth, I do think of it as a spectrum where one end of the spectrum is wearable device data and the other end is smartphone data, where the smartphone data, you kind of have more plentiful. What I mean by smartphone data in particular, I'm referring to passively collected sensor data, like the GPS, accelerometer, screen on off, etc. And this data is perhaps easier to collect because, and I'm a big advocate of not providing study phones where needed, like instead taking advantage of the fact that there's like smartphone penetrance across socio-demographic status. And because if you're providing a phone now, you lose their intrinsic motivation for using the phone. The idea is you want them to use their phones they would normally live their life without altering their behavior at all, because if you're asking them to do something different than what they would normally, that will really hurt you if you're trying to track them or have them be in your study for a long period of time. It will really hurt adherence if they're not using them and they're not completely intrinsically motivated to be using them. So when I talk about the spectrum, basically you get a lot of data that, but the problem with it is that it's often very messy. It often has way more missingness than you get from wearable devices. Often, and if not missingness, sparsity. I'll get into the distinction between missingness and missing data and sparse data in a moment. But in some sense, right? The primary purpose for a phone, when someone purchases it for themselves, is not to be a part of their study. It's, I don't know, maybe to, phones have morphed into much more than a communication device, but, it's maybe primarily to communicate with people, and secondly, to surf the web and, I don't know, play games, consume media, and then way down the list is going to be a part of your study. So, in practical settings, most of the time when we collect data, first of all, we have so much missingness because we are not turning their sensors on 24/7. If I turned on someone's GPS for 24 hours a day, and also their accelerometer, which is going at like 10 hertz, 10 measurements a second, yeah, you get a lot of data with no missingness, but their battery life would go from 12 hours to 2 hours, and then they would immediately uninstall the app and leave your study after one day. So most apps in this space will impose various like sampling techniques to collect data sporadically, whether it's interval sampling, where they'll just say like, okay, we're going to turn on the GPS for a minute every 10 minutes. So we just kind of get a rough ping of, you get a good sense of where people are over the course of the day, but you're not going to be able to map them onto like their actual mobility trace, their second to second movements generally, right? And so that can be fine if all you want to do is calculate a daily summary, like how much time are you spending at home, for example. Well, anyway, I can go on this tangent for a while, but not get too far away from this. This spectrum of smartphone data to wearable device data, I think the spectrum is very much so that you get like high amounts, like large quantities and potentially for longer periods of time of messy data that has a lot of missingness. So that's the con, as opposed to wearable device data where you get really high quality data, much less missingness. Now, anybody who's worked with wearable device data knows you still get missingness. But it pales in comparison to the kinds of missingness you get with smartphone data. And But the problem with wearable device data, of course, is that now you have to make them wear this device. And just there have been so many studies that have looked into this, that regardless of your incentivization, regardless of, at the end of the day, people are not going to stick in a study, or not going to wear your device really long term. What I mean is, like, what if you want to follow someone for a year? It's just impossible. It doesn't matter how much you pay them. People will drop out of your study when they're not intrinsically motivated to be wearing these devices in the first place. Okay, so I realized that all of that was kind of a tangent compared to the slide that I'm showing you right here. But so back to the topic at hand. I've talked about how there's important day-to-day and within a day variability. And so what's nice about collecting these wide domains of behaviors, that you're able to kind of paint a tapestry for each individual of what I mentioned, that, we can measure things like mobility using GPS data, or physical activity based on the accelerometer. You can do like step counts and things like this. We can also look at routine based on how they're using their phone over the course of the day. So all of these are perhaps really important types of behavior. And rather than painting someone in a corner and just saying, like, okay, you're a binary depressed or not, right? Which there's a lot more heterogeneity in that diagnosis of depressed. It's like, why are you depressed? In what domains are you, is your depression being manifested? And so it's really important to have like a wide view, a deep, wide view of a person, rather than putting them in a single box. And that's kind of what this is supposed to demonstrate. In the case of depression, maybe there's like 3 different ways you can be described as being depressed. And so if you bundle them together and do like a case control, like logistic regression or something, this is why, primarily seem to be why when, initial studies, when we first were doing GWAS like 20 years ago and whatnot, we had family-based studies that were giving us like high heritability estimates in a lot of these mood disorders, like such as depression. But then when we did these huge cohorts of case control studies to try, we would end up not being able to discover genetic variants that were just explaining only a fraction of what we knew existed with respect to heritability. And a big reason for it is this, right? If you group everyone, even if you have 10,000 people, 5,000 cases and 5,000 people with depression, if you do just like a logistic regression and call them all the same, well, when in fact there's a lot of heterogeneity for why they might be feeling that way, you're dampening your signal. It's the wrong model. And it's not a surprise that we would not end up fully explaining the heritability. So like, this is something that we maybe learned, was maybe shocking at first when we were doing the first genetic studies in some of these complex genetic diseases. But this makes us think, okay, maybe we need to take a different view on the phenotype side of things. And this is where wearable devices and smartphone data can help. Okay, so I already kind of talked at this, and I'll jump over this, especially for this group. I don't need to go into too much detail, but at least the work that I do in my lab does, I really think of smartphone data as coming from, and I think the same applies for wearable device data, but I'll talk about the caveat for that in a second. I really describe the research as happening in 2 phases. The first one is going from the raw data, like the sensor data itself, and modeling that.
Ladies and gentlemen,
either accounting
this is the final boarding call
sorry, that's
for
big.
Alaska Airlines Flight 3496 with service to Seattle. All passengers should now be on board through gate E83.
Okay.
Mesdames et messieurs, ceci est l'annonce de l'embarquement pour le Alaska
Through this. Can you guys still hear me fine?
6 à destination de Seattle.
Hopefully this will be done
It's
in
hard.
De se présenter immédiatement à la porte 83.
Yeah, it's hard to hear you over the announcement, but yeah, when you move
Okay.
closer, it gets a little bit better.
Okay, I'm so sorry about that. This is the reality of I wasn't able to plan for this in advance, but we'll make the most of it. So where was I going with this? Right, I was describing there's like kind of 2 phases of analysis here. The first one is going from the raw data, which has a lot of missingness in it. And also it's not really interpretable, right? Like over here for GPS, we get these like latitude, longitude pings with a timestamp, and then an accuracy measure, for example. Like that's what the data looks like, but that's not really used. It's not ready to be modeled directly and related to something that's clinically relevant yet. So we need to, for example, maybe turn it into like a daily measure of how much distance traveled today, how much time did you spend at home, and quantify how your routine matched how you moved and when you moved throughout that day and whatnot. So that first stage of going from the raw data to an interpretable measure of, say, mobility, that is not trivial. There's going to be a lot of missingness. We got to model that. We have to have a good imputation model for it. And these are things that like my group has developed, basically going from this raw data. And I would actually say most of my work is focused on this first phase, which perhaps is not, at a high level view, it doesn't seem as exciting because we're not yet even talking about the clinical outcomes yet, right? It's like, okay, now I'm trying to estimate these 15 interpretable measures of a person's mobility over the course of the day. And the models that lead to that are really important. And so that's what this is kind of indicating, is that the phase that goes from the data on the phone itself down to this nice, pretty data frame. So for this data frame, you can kind of, I don't know if you can read this, but each column here, you can think of it as a day, and each row is like a different feature. Now we actually do, our pipeline has more features than what you see here, but this is just to demonstrate, and the colors are demonstrating kind of what they're reflecting. So like, for example, I talked about sleep, but the sleep features are not showing up here. This is just a demonstration of like what the nice, pretty data frame looks like. And so this is from an actual person with schizophrenia, where, you can kind of see this matrix represents daily features over the course of the study or over the course of 5 weeks for one person. And we have this for everybody in the study. So going from that raw data to this is that first phase that I'm talking about. Now, once we have this, relating this back to our clinical outcomes, maybe to predict something like hospitalization, or do change point detection on this, or do longitudinal modeling on this data frame, on these data frames across the sample. Like this is that second phase where this is the more, classical predictive modeling, statistical modeling, machine learning, longitudinal modeling, time series analysis. When we think of the data analysis, that happens once we have this data frame. But I just cannot underscore the importance of this first phase. It's not trivial to go from the smartphone to this data. And that's actually probably where most of my and my group's contributions come to play. So yeah, this is just a closer view. Again, we do have more features than what you see here, but just to demonstrate how these are, for this particular study, there was 3 self-reports a week, and you can see how, it's kind of irregular when you see these two, perhaps this survey was prompted on the previous day, but they didn't answer it on the phone until the following day. So it appears aligned. But you can kind of see that self-report in general is going to be much more sparse, whereas we have almost complete data here after we've done our imputation, and these are all coming from the passive data, whereas we call this actively collected data because it requires participant involvement. Now these zeros are probably true zeros. They just didn't text anyone that day. So this is not missing. Like we think of this as we have complete data here. Sorry, our features are complete, and guaranteed there was missingness in this GPS, which we have modeled out and we imputed. But yeah, just the distinction between the passively collected data and the features derived from them and the actively collected self-reported data is really huge. Yeah, so over here, the self-report, we do treat that differently. Often this is where our outcomes are coming from, and we're trying to predict this with the passive data. Now, I'm kind of getting into the second phase analyses right now, but why are we, generally, if you think of your Y in your analysis, it's here, and our X's are coming from here. Now the reason for it is precisely because these are passively collected. It's more plausible that we can collect them.
It got really quiet again. Can you lean in a little more?
Yes, I'm sorry. Okay. How's this now? Can you hear me
Say
fine?
something again?
Yeah.
It's a little bit weak. Yeah.
Hold on one second.
How to do something when you moved.
Okay. Yeah, I'm actually seeing my mic is not lighting up as much when I'm talking.
That's better,
That's
much better.
That's strange. Okay, I'm looking at my volume here. Okay.
You're coming through loud now. I mean, it's cutting in and out sometimes, but it sounds great now.
Okay, I'm so sorry about that. I will also, you know what I'm gonna do? I'm gonna disable my video for now in case it's like a bandwidth issue. Okay. All right. So let's see. I was talking about the distinction between passive and active data and how generally when we model it, now I'm talking about that second phase of analysis, we're modeling the self-reported outcomes with the passive data. And the reason for that is because in many cases, actually, I'll be showing some examples from a study from one of my collaborators who collected self-report intensively for 2 weeks, but then we wanted to follow them for more than 2 weeks, but we just couldn't expect them to keep answering self-report for more than those first 2 weeks. And frankly, even if, as I mentioned at the start, people, it's very hard to keep someone engaged in a study over a long period of follow-up, especially if it's requiring a lot of active input and self-report. So in this study, one thing you can imagine is if you follow someone and you get both the Y and the X over, say, 2 weeks, that's enough. If you can build a predictive model, then maybe 6 months into the study, when you only have X, you can predict what their Y can be. You can like train your model when you have both, whereas it's much more feasible to observe your features derived from passively collected data at the 6-month mark or at the 1-year mark or long term. So that's, I think, the motivation for why we generally try to model the self-reported variables as an outcome, all based on the passive data. That is the dream. And it works well in some scenarios, as I'll show you. Well, actually, I'm not going to show you the cases where it hasn't, but it doesn't always work. Okay. So I realize also I've been kind of going a little bit, I'm not gonna be able to cover everything I have in these slides, but I'll just give, I have basically throughout the rest of this talk, I actually talk about a couple different approaches that those phase 1 models going from the raw data to measures, meaningful measures of behavior. Then I also talk about some of that phase 2 relating to clinical outcomes. So maybe I'll just cover a couple of those cases. I won't be able to get through everything.
Ian, you're a little bit quiet. We kind of lost you there for a second, a little bit for the sound.
I see. Yeah, I don't know. Sorry. No. I'm seeing that my mic is, I don't know why my mic is not picking. It's very sporadic. Maybe it is the internet. Well, I'm keeping an eye on it, so I kind of know when I'm not going through. But right now it looks like it's quiet.
You're good now.
Yeah, we can hear you well.
Okay. I'm trying to stay close to the mic. Okay. So let's see. The first approach I'll talk about, the first example, is how we measure sleep with smartphone data. So I'll talk about what I think I'll do is I'll cover this example and then I'll jump ahead to one of the phase 2 analyses where we take some of the features and relate it back to clinically relevant outcomes. So I'll start with this kind of phase 1 analysis. So here's the idea is we wanted to take the smartphone's screen on off data as well as the accelerometer data, and we wanted to infer sleep. Now, there's a lot of challenges with this. And actually, the approach, we published a sequence of papers that ultimately went into this method. But the challenges are, I like talking about this example because this is a prime example for doing imputation on the data. Because screen on off data, this is metadata that your phone collects that says like, okay, you unlocked your phone at this timestamp and you locked it again at this timestamp, or like basically when is the screen on? Now, this data is never missing. It is always collected. Basically, if there's a long gap, if there's a long period of time where we don't observe any missing data, or any screen use, that's a true zero, right? This is a case where the data we ultimately collect is entirely present. It's complete data. Now, on the other hand, accelerometer, I mentioned this early on, there's a lot of missingness, oftentimes by design, because we don't want to burn the phone battery. So, in most cases, there will be some kind of interval sampling scheme where you collect for 10 seconds and turn it off for 10 seconds, alternating while the phone is on. And there can also be cases where there's like native operating system power saving measures that will override our app that's collecting the data, and you'll get even longer periods of missingness. In any case, accelerometer data often has lots of missingness, while screen on off data does not. Now, the next thing, if we're thinking about imputation, is, okay, can we try to impute some of the summary measures of the accelerometer data based off of screen on off data? Now, there is no way we can impute actual accelerometer data itself, which is, forces in an X, Y, and Z direction. Essentially quantifying the acceleration in these directions. It's quantifying the force. And so we can't actually impute the raw accelerometer data itself just with screen on off data. But if we were to say bin data by the hour, and we looked at, okay, how often were you on your phone over the course of that hour based off of screen on off data, it should be strongly correlated with, say, the average magnitude of the accelerometer. So, the average magnitude of the acceleration that your phone was experiencing over the course of that hour. And indeed it is. If we look at times when both data are present, there is a strong correlation there. And so this is a perfect example for using an imputation method, where we, in this case, we're not actually imputing the accelerometer data itself, but maybe we are imputing the average magnitude of acceleration over a binned time, like an hour. So that is actually what we've done in this case, is where we take these two data types. And why am I focusing on these two data types? Because again, the ultimate goal here is that we're trying to get estimates of sleep. And we're going to try and get at that using the phone. And so what I've just addressed right now, this imputation method that we have, this gets at the missing data. Now, that's not the only problem. This is where there's a huge distinction between smartphone data and wearable device data. If we just used your smartphone and said, when were you actively using your smartphone? And then we said, okay, when you're not using, we're going to look at these nighttime hours where you're not using your phone, and then use that to kind of infer when you're sleeping. What you end up doing is you severely overestimate sleep, because you're making the mistake of assuming that the phone is the person. And I don't know about you guys, but maybe I'll set the alarm on my phone and put it on my bedside table, and I might even get up. I might even go about I won't be necessarily closing my eyes and going to sleep the instant that I put my phone down for the night, for example, right? And that's just someone that's if I'm using my alarm at all, right? There might be people who get home from work and they put their phone down, plug it in, and they don't even touch it until the next day. Who knows? People use their phones differently. And if you make the mistake of assuming the phone is the person, you never underestimate sleep, but you will always overestimate sleep. So we do address this. But to start with, we do handle the missingness. And then bridging the gap between the person and the phone, I'll talk about how we handle that in a couple slides. So the first thing we do, though, is that we try to estimate at this hourly level. We have this latent state for whether or not you're kind of actively using your phone or not. And that's over here. You can kind of see this kind of circadian pattern. Now, the reason we model it this way is because for each person, we also have these random intercepts for each hour of day. Basically, if we follow someone for a long period of time, maybe between 1 and 2 a.m., you're almost never on your phone. What that will result in is a very negative random intercept, which basically says, oh, you're likely to be, if you're not already in the inactive latent state, you're going to transition to it soon. So we do this kind of alternating model where we alternate. There's like a rate of change going. It's like a two-state model. You can think of it that way, where if you think of like a Markov chain between these two states, essentially we have this model where if you're never using your phone between 1 and 2, then if you are in the active state, we're going to have a very high rate of change to the inactive state during that time. Long story short, these random intercepts, we have like 24 random intercepts per individual, which kind of correspond to, which roughly map to when they are actively using their phone and when they're not using their phone. So for this is real data from a person. You can see that, like, for example, in this case, the B1 model is the transitioning from active to inactive. And you can see that right after midnight for this person, for these 4 hours right after midnight, what this is basically saying that if they are using their phone during these hours, there's a very high rate that they quickly go to inactive. So it's like, it roughly corresponds to when they're going to bed. Or if you wake up in the middle of the night and use your phone, you immediately stop using it again. And then if you look at, say, let's see, at 8 a.m., oh, they're waking up at 8. The transition from inactive to active is very high. So there's like a mapping between kind of their routine, their nightly routine. You see it really plainly here. Also, you'll see that these are, there's like a 24-hour cadence here, then it repeats, right? Because we model these hour-of-day random intercepts that in our modeling assumption, we assume holds over the duration of the study. Now, there are probably weekend and weekday effects, and we can capture that separately. But this gives a really good sense of a person's routine. Now, one thing that we wanted, this is all in service of ultimately quantifying sleep. But along the way, we can actually get other measures of behavior that are important. I'm going to point to one immediately. What if you model this for a person and all of their random intercepts are just a flat line? What's the implication of that? The implication of that is that they don't have a routine. They're like, they'll go to bed at 4 p.m. one day and they'll go to bed at, 2 a.m. the next day. There's like, they're using their phone equally over the course of a 24-hour period. No one's actually like that. But I'm just talking about one extreme. If these random intercepts end up having no information in them, if they just correspond to a flat line, that really means that there is no like hour of day tendencies for how they're using their phone on a day-to-day basis, which would be absolutely absurd if it was actually flat. But this gives a suggestion of, if you want to see how strong someone's routine is, there's a nice mapping between the strength of someone's routine and the variability in the y-axis of these hour-of-day random intercepts for each person. So this actually, even though this wasn't the ultimate goal, along the way we thought, hey, this is actually would be a neat measure of strength of routine for an individual, trait level quantification of a person's routine. So we actually call that variability of these random intercepts, we call that the ARM, the activity rhythm metric. I'm actually going to jump ahead before I get back to sleep and talk about this kind of intermediate feature, which quantifies a person's routine based off of this is a derivative of accelerometer and screen on off data. And so I'll come back to this a bit for the sleep estimation question, but I want to let's talk about that ARM I just mentioned here. So what we wanted to see was, okay, let's take this ARM and so I'm jumping ahead to how we've used it to connect it to see if it's related to anything that's clinically relevant. So we took the ARM and then we said, okay, in this study, is it related to, say, self-reported sleep duration? Do people who, based on their passively collected data, have high degree of routine, so that's people who rank really highly on the ARM, do they also tend to sleep more? And we saw that indeed they do, pretty strongly actually, because it's to get this level of significance with, I think this is like 30 or so people, and you can kind of visually see the trend. Now, I wanted to also give an example. I was talking about these 24-hour random intercepts. This is someone who has a low ARM. This is like when I'm talking about someone who almost has no routine. And these are 3 different individuals from the sample that demonstrated different degrees of routine. So we looked at things like, and there wasn't, again, there was very low power in the study because it was only, I actually don't remember the sample size, but if you count the number of points here, it's like 30 or so, maybe 40. So in some cases, like we weren't getting significance, but so in this case, like this is the Beck depression index and we didn't get significance, but there probably is a relationship between routine and this is the Beck depression index. But we just don't have power to detect this in our study. But for the ones where there was like a strong, I guess in our sample, for whatever reason, the men in the study had a much higher routine or strength of routine. So, you know, there were some interesting things to look at. I don't think a lot of what we saw was fairly intuitive with what we expected in terms of the relationship between the strength of routine and some of these outcomes. It looked like older people had stronger routines than the younger people in the study. But anyway, so I just wanted to show the goal of this was not to derive necessarily a measure of routine, but we picked that up along the way and found out that it was actually, you know, it was kind of matching the eye test for what we would, it seemed to be measuring what we expected it to measure. But let's not lose track of the high level. We're trying to estimate sleep from this. So the purpose of doing this latent state estimation is that once we've done this, this is a way of accounting for missing. Now we need to relate this to sleep. So you might think, okay, now that you have this model, you can go ahead and take the latent state estimates for a given night and use that to infer sleep. But notice I called the states inactive and active phone use, right? And I gave the example that that is not necessarily sleep. And if you treated it like sleep, if you treated inactive phone use as sleep, then you would severely overestimate sleep, and you do. So jumping ahead, what happens if you have a night of data like this, for example? This is actually just screen on off data from over each row here is 1 day for a person. So you can see this person used their phone and then they stopped using it here at like midnight. But then the following morning, they didn't use it at all. Are we going to say that they slept? Like what happened here? Are we going to say they slept until noon? No, they probably just didn't touch their phone in the morning. So if we had a sleep estimation method that rigidly looked at the data and said, okay, the phone is representing the person, then you'd kind of like would draw a line here and say, okay, you went to sleep here and you woke up here. And we're just not accounting for the discrepancy between a person and their own phone. And the behavior of the person is not the behavior of the phone. There's a correlation there, but that's not the same. So how are we going to account for that? So here's where we actually use a semi-supervised approach. We get some self-report from a person where we should have some, if someone tells us, for example, I go to sleep on average at midnight and wake up on average at 8, then you know what? When we fit our model using only their passively collected data, we better arrive at a model which is kind of empirically aligning with that. If we are empirically going to say that, okay, our model is saying that you actually sleep 10 hours on average, when you self-report that you sleep on average 8 hours, then there's probably a problem with our method. So our semi-supervised approach essentially will penalize our deviation from a very small amount of self-report that a person gives. It could even be a single measurement. It could even be that one measurement from the PSQI. Now, and we do this with we essentially add a penalization term to our model that will penalize deviation from that self-report in our empirical data. Now, I want to show like an example. This is from a different study with one of my collaborators at Beth Israel, who had actually, this is from a really big study of like 500 college students that was conducted over COVID. And I want to just show a couple examples of if we did sleep estimation with our method versus a method that does not account for the fact that the phone is not the person. So if we're just assuming that the phone is representative of the person's behavior, remember, we should expect to see huge overestimation of sleep. Now, when we look at these plots, in this study, they actually only would do weekly questions of when did you go to bed on average over the previous week. And so this is like a snapshot from this one person over 2 weeks. So you can see that they said, oh, I went to bed on average here, and I woke up on average here. And they actually said the same time 2 weeks in a row. And just to kind of overlay what our actual nightly estimates of sleep are. And remember, this is where, there can be night-to-night variability. The question that they answered here was, when did you go to bed on average? And when did you wake up on average? So again, it would be, if we had nightly estimates, it would be better. But this is just, based on the eye test, can we just see what happens if we, under the two approaches? So this is the no adjustment for self-report. This is the standard approach, which should be overestimating the bias. And what happens if we add the semi-supervised approach into the mix? Notice the change here, right? It kind of, maybe this is an example of a morning where they didn't use their phone at all. And so if we assume that they were sleeping, this is probably wrong. They probably did not sleep 14 hours. Very few people I know can actually do that. Actually, is that even possible? I don't know. But they most likely did not sleep 14 hours here. They probably just were not using their phone. Now, suddenly that vanishes when we start doing the semi-supervised approach and things look a bit more reasonable. Here's an even worse example. Here's a different person who they very seldom use their phone. So this is what we call very sparse data. It's not necessarily missing, but it's sparse. And if you don't do any of that adjustment, if you use a standard approach, which was maybe developed just for wearable device data or something like that, where there's the relationship between the device and the person is much tighter than what you get with the phone, you get crazy estimates of sleep. This is way too big. I don't even know, what is this, 19, 17, that's 16 hours of sleep this night. There's no way that is right. And when we do the semi-supervised approach, it really tightens it up and becomes a lot more realistic. So I will say that, of course, compared to like gold standard estimates of sleep, this pales in comparison. We're not doing polysomnography, but in this case, we're just trying to get like a rough ballpark estimate of, can we get your right sleep duration estimate within 30 minutes, give or take, right? We're not like looking at, this is a much coarser measure of sleep, but still important. So if we did our adjustment in this case, revisiting this one, what you can imagine is that, well, with a semi-supervised approach, we could learn from this person's history and maybe say, you know what, they were probably awake at this time. I'll skip over this one. I wanted to just say we analyzed this, averaging it over, we applied this to everyone in the study, and we basically, based on the self-report, we could say, okay, when we do have self-reported sleep, how does our method compare with that's only using the passively collected data? And the units of this are in hours. So you can kind of see that what actually ends up happening is that our approach, ultimately, the semi-supervised approach, we were off by a little more than, what is this, like 35 minutes or something? Oh, sorry, another announcement. I'm almost done here, though. Bear with me for this announcement.
Los Angeles. Customers who would like to volunteer to have their carry-on baggage checked to their final destination are asked to see the gate agent at this time.
Okay, I think we're going to get the announcement in French.
Bord du vol Air Canada 554 à destination de Los Angeles. Les clients qui souhaitent se porter volontaires pour faire enregistrer leur bagage de cabine jusqu'à la destination finale sont priés de s'adresser dès maintenant à l'agent de porte.
Okay, I'm so sorry about that, guys. Again, this is somewhat unavoidable. But as I was saying, ultimately, we only get off in terms of sleep duration by about, what is this, like 35, 37 minutes on average. Whereas if we were, you're kind of overestimating sleep in this case by like 2.5 hours or up to 4 hours, depending on the method you're using. But when you add the penalty, it just really cuts down on the bias a lot. And it becomes usable. If I was giving these estimates to my clinical collaborator, they would look at this 17 hours of sleep and just say like, this is absolute garbage. I don't trust the method at all. But when I give them this, it becomes, and we do see that it kind of validates and aligns with the self-report a lot better. Okay, I realized that I only covered kind of 2 of the applications, but I did want to cover a phase 1, which was the estimation of sleep itself, and then also connecting it to clinical outcomes. I will just say at a really high level, we've also done things like change point detection. Once we have that data frame, multivariate change point detection. In fact, I have an R1, which is basically focused on this phase 2 of how do we relate through multivariate change point detection, connecting this back to clinical outcomes. So, for example, in this case, there was someone who relapsed and they had schizophrenia, and we were able to, in this study, we found that we had significant change points in the week prior to relapse based purely on the features derived from passively collected data. There was a much higher rate. I think we had like a 72% increase in anomalies and change points in the previous week leading up to relapse. And the implication here, of course, is that just by looking at how someone is using their phone and looking at the passive features without asking them anything, it's really informative about behavior that actually connects to something that's really clinically relevant, in this case, hospitalization due to relapse. So I thought this was a really exciting study, and I just covered it at a really high level. We also we have a sample size calculator for if you want to run your own smartphone-based digital size phenotyping study, because it's, you have to think about how your sample size in addition to duration of follow-up. So, and all the power and sample size considerations that go into that. This is a paradigm of longitudinal data analysis, which is actually outside of what classical statistical longitudinal data analysis covers. So in the classical longitudinal data analysis context, we consider large sample size with short follow-up duration periods. So think of like, clinical trials in like the 80s, 90s, and even now, where there might be like yearly follow-up. And so a lot of the longitudinal methods, such as GEE, are designed for that. And these assumptions fail in this kind of flipped context where you might actually have a small sample size, but you follow someone for years. And if you're using daily features, that might be like 365 repeated measures from the same person. So it's kind of flipped. It's a lot of measurements per person, but there might be few people. And here a lot, we've kind of shown that some of the classical methods will fail. You get really terrible GEE performance and whatnot. So anyway, we have a paper that really dives into these considerations of how you should handle data collected from these kind of studies and doing with an accompanying Shiny app if you want to do sample size calculations yourself. I also do some work with like neural networks and longitudinal neural networks. I'm going to skip over that just because I realize that we're pushing up on the hour, I believe. So I will stop there. Again, I do apologize for the interruptions throughout, but we do have a few minutes for questions. Hopefully there'll be no more announcements in the last 5 minutes.
Great, that's amazing. Thank you, Ian. I'm going to pause and open up the floor for questions.
Hey, and great talk. I'm wondering, what are your top 1, 2, 3, however many you want to give, mistakes you see sort of moderately informed people making in these kinds of studies?
Oh, yeah. That's a great question, actually. I don't normally get that question, but there definitely are quite a bit. I would say going into it, underestimating the amount of missingness that is encountered in the data. It's sometimes really extensive. And so I cannot understate just how important it is that you handle the data right. So there's a lot of people that will like enter into the study and be like, wow, this person must have had their phone off for like 2 days. And like, what do I do with that data? Or lack thereof? Or maybe I've collected other data, maybe there's multimodal data that I have, but these data streams are completely absent for like really long periods of time. And I think there's just a lot of people that get kind of shocked by that and they don't know how to handle that. So I think that's perhaps the number one, is maybe underestimating the quality of the data when they start doing things like smartphone studies. What other mistakes? I would say perhaps being a little bit too eager about doing self-report and expecting too much. So like I actually see this in a lot of my own grant review of these kinds of studies where people will way overestimate participant adherence in the long term. They're like, okay, I'm going to ask, 4 questions a day and I'll ask for like a month. And I just know that guarantee, and I'll look at the sample size calculations and they'll be like, oh, maybe we'll have like 80% people that hit that mark. And I'll be like, there will be 0% of people that hit that mark. You're not asking someone 4 times a day for a month, and they're like, no one does that. No one is going to be that adherent. And so I would say that's the number 2 mistake. All right. If someone else wants to ask a question, I'll mute myself for this announcement.
So this is, I think, something of a general level question, kind of like Dan's about study setups, but I'm curious what you see as sort of the direction in using a lot of the accelerometer data or passive data and doing mediation or moderation analysis sort of for other clinical endpoints as part of other studies, right? So maybe you're setting up a trial and you're tracking something and you just want to tack this on top. Like, one, do you see it happening? And 2, what do you see as either mistakes or benefits or what's working in that space?
Yeah. Actually, this is something I've thought a lot about because I, of course, advocate for adding like smartphone data collection arms to studies. How I've kind of approached it is actually the selling point. I make it based purely on the self-report. My interests are primarily in handling and using the passive data. I think that's really interesting. I do think that especially people who don't have exposure to the mHealth space so much, that's not necessarily of interest to them, or they don't like maybe see the potential or factor that in yet. And so how I take the approach is like get your foot in the door by advocating, hey, like self-report via smartphone is really straightforward. You can ask, at any time of day. It's very easy to send. And like I think that's a great selling point, is selling them on the self-report. And then after the fact being like, as an aside, like you can also collect this other data and we'll, tune it way down if you want so that like it's kind of minimal data that's collected so it really doesn't impact user experience and battery and whatnot. And like we can use that if you want. And then I think what will tend to work is that you then kind of say like, oh, by the way, here's daily estimates of sleep. Here's daily estimates of distance travel. Here's how many people they talked to today and whatnot. And once that matrix, that colorful matrix I showed you is in hand, then people's imaginations can start to run away. But definitely, I think that like the entry point with my collaborators that has worked better has, rather than saying completely redesign your study around the kind of data that this is giving, go into it and maybe as a secondary analysis, we'll talk about these like digital biomarkers and how you can use them. But really sell them on, can you imagine a study that is getting self-report through the phones? And once that happens, I think that's a slippery slope into just fully embracing this digital phenotyping paradigm. I don't know if that answers your question.
No, I think that answers that gives me a lot to think.
So I'll say like right now, actually, PMARC is a center at Penn. I don't know how many of you guys are acquainted with PMARC, but it's mental health for HIV. What does it stand for? Mental health HIV. I actually know what it stands for. I'm one of the co-directors for the MET score, but the new wave of studies that we're rolling out, I kind of took that approach where I was like, hey, what if we did self-report via phone? And you can also collect some of these other data, but really, like, look at what you can do with the self-report. And so I'm kind of excited to see what we can do with the new wave of, and that was kind of enough to be like, all right, I think everyone got on board with that idea, and I'm kind of going to be excited to show them like what else you can do with all of this, secondary passive data that we'll be collecting. So that's been a successful model for me when it comes to having people transition from more traditional data collection to tacking on smartphone arms to their own studies.
Awesome. I think we're out of time. We're past our time. But I want to thank Ian and everybody else for showing up and listening to Dr. Barnett's talk about passive data use. And yes, our next meeting will be March the 25th. And there'll be information sent out about that shortly.
Thank you.
Thank you, everyone.
Thank you. Safe travels.